next properties which are differentiation properties. Okay, we'll see differentiation and integration properties. Okay, so let me call it as differentiation property. Okay, so before we go into the property, so let us first understand what is differentiation. So for any signal x of t, we have seen that derivative is defined as what here? Y of t equal to d by dt of x of t. Okay, but we have studied in our school days that the definition of derivative is given by limit h tends to 0 x of t minus x of t minus h divided by h. Correct. So this is the way how we define the derivative operator. Okay, but we can easily prove that the differentiation operation is linear and time invariant. Okay, so this fellow is linear and time invariant. Okay, so we can easily prove that, and hence what is that we understand, because it is linear and time invariant, we can LTI system implies we should have impulse response, and the output of LTI system should be what? It should be a convolution operation. Okay, so let us write down this in block diagram notation. So we have x of t. Okay, so we have a differentiation operator d by dt. So and we get what as output? Y of t, which is equal to, I don't say y of t, I just say d by dt of x of t. Okay, and just now we have seen that this fellow is linear and time invariant. So because of that, we should know what is the impulse response of the differentiator. Okay, so this we call it as what? Differentiator. Okay, we call this as differentiator. Okay, so we want to find the impulse response of the differentiator. So to find the impulse response, what should we give as input? We should give impulse as the input. So if we give delta of t as the input, what will be the output there? What will the system do? System will, whatever input you give, that system will differentiate. So if you give impulse, that fellow will differentiate the impulse and will give you delta dash of t as the output. But this is the response of the system if you give impulse as the input, and hence this is the impulse response of the differentiator. Okay, so impulse response of the differentiator is how much here? Delta dash of t. Okay, so that is important. So let us write down again the block diagram notation. So x of t. Okay, so you pass it through differentiator. Okay, so x of t, you pass it through differentiator. What do you get? So if you pass it through differentiator, you get d by dt of x of t. But what is impulse response of the differentiator? What is impulse response of the differentiator? That will be equal to delta dash of t. Okay, the impulse response of the differentiator would be delta dash of t. Okay. So now let us see what will happen if you have a double derivative operator. Okay, so now let's assume that we have y of t equal to d square x of t divided by dt square. So this we can write it as what here? d by dt of x of t. So this implies that we are doing double derivative operator. Means what? You do first differentiation and then we do one more differentiation. So definitely this is what? Cascade of two differentiators. So we write like this: x of t is passed through first differentiator, so d by dt, and then you again pass it through second differentiator. Okay, so you get finally d square x of t by dt square. Okay, so what is that we have got? So first differentiator will have delta dash of t as the impulse response. Second differentiator also will have delta dash of t as the impulse response. So what will be the overall impulse response of the double derivative operator? Okay, so let us call that as h of t. So overall impulse response of the double derivative would be h of t would be equal to delta dash of t convolved with delta dash of t. That would be the overall impulse response of the double derivative. But if you look at the double derivative operator as a single block diagram, means x of t is passed through double derivative operator. So d square by dt square, and output would be again d square x of t divided by dt square. So what will be the impulse response of the double derivative operator? Again, you have to give delta of t as the input, and what will be the output here? If you give impulse, what will the system do? It will do the double differentiation of the input, which is impulse. So you get delta double dash of t. So this would be the impulse response of a double derivative operator. But from previous discussion, we have seen that impulse response of double derivative operator is also delta dash of t convolved with delta dash of t. So this implies what? Delta double dash of t is same as delta dash of t convolved with delta dash of t. Okay, so delta double dash of t equal to delta dash of t convolved with delta dash of t. So with the same argument, we can see that what happens if you differentiate delta of t m times and then convolve with delta again differentiation of delta of t n times. So what will be this equal to? So if you pay a little bit attention, you can see that there are m differentiations here followed with n differentiators. So I will write down that. So means what? You have x of t, that fellow is passed through a cascade of differentiators, correct? So a cascade of differentiators like that. How many are there here? So in first case we have m of them, and then we are again convolving with delta power n of t. Means what? Again there are n differentiators, okay, and they are also in cascade. So what do you get? You get a cascade of n differentiators. So finally you get y of t as the output. Okay, so what will be the overall impulse response here with the previous argument, whatever we have done? So what will be the overall impulse response of this cascade of differentiators? You will get that as h of t equal to, first fellow will have delta power m of t convolved with delta power n of t. But we know that like that we have how many differentiators in cascade? So there are m plus n differentiators, and hence final answer would be delta power m plus n of t. So the overall impulse response of cascade of these differentiators would be delta power m plus n. So what will you get? So delta power m of t convolved with delta power n of t would be delta power m plus n of t. So in that way we can get the impulse response of the many number of differentiators. Okay, now let us come back to differentiation property. Okay, so what does it say? If y of t equal to x of t convolved with h of t, okay, then our question is what will be dy of t by dt? That is the question. Okay, but just now we have seen that differentiation of any signal is what? It is convolution of that particular signal with whom? Delta dash of t, correct? So dy of t by dt can be written as y of t convolved with delta dash of t. Okay, so but we know y of t to be equal to how much? X of t convolved with h of t. So this should be equal to x of t convolved with h of t, and this fellow is again convolved with delta dash of t. So what will be this equal to here? Because of associative and commutative properties, we can have two results. One is x of t convolved with these two guys. So h of t, if you convolve any signal with delta dash of t, we will get that signal's derivative. So you get d by dt of h of t. This is one case. Or you can differentiate, or you can convolve these two guys, x of t convolved with delta dash of t, and then you can convolve with h of t. So x of t convolved with delta dash of t is how much? D by dt of x of t, and this is convolved with h of t. So in that way we can get what? So we can get the differentiation of the output of an LTI system. So note that if you want to differentiate y of t, you have to differentiate any one of the signals, either x of t or h of t, not both. Okay, so if you want to see this in block diagram notation, what is that? We have an input x of t and that is passed through an LTI system with impulse response h of t. So we get y of t, and then this is our y of t, correct? So we get what? We get y of t, and this y of t is passed through a differentiator. Okay, so this y of t is passed through differentiator, and final output would be dy of t by dt. Okay, and this differentiator will have what as the impulse response? Delta dash of t. So what will be the overall impulse response of this system here, the dotted system, because we have a cascade of LTA system followed with differentiator. Overall impulse response, let me call it as HO of t overall. Okay, so that should be equal to h of t convolved with delta dash of t, and again we know that that is nothing but d by dt of h of t. Okay, so overall impulse response of this cascaded system would be d by dt of h of t, which is derivative of impulse response of the system. Okay, so we will take a small example here where we can use the property of differentiation. Okay, so let us say if y of t equal to, let me say, e power minus 3t u of t. Okay, so convolved with, let me say, u of t plus 1 minus u of t minus 1. Okay, so y of t is this, then what do I say? dy of t by dt is equal to dash. So question is, what will be dy of t by dt? So this, according to our discussion before, this is nothing but y of t convolved with delta dash of t. Okay, so this is equal to how much here? E power minus 3t u of t. This fellow is convolved with this signal, which is u of t plus 1 minus u of t minus 1, and this is again convolved with delta dash of t. So your wish, whichever you want. So you can convolve e power minus 3t u of t with delta dash of t, or you can convolve these two signals. Okay, so which is easy? Convolution of the last two signals is easy. Why? We know that derivative of unit step function is Dirac delta function. So this should be equal to e power minus 3t u of t convolved with you get, we are using distributive property. What do you get here? D by dt of u of t plus 1 minus d by dt of u of t minus 1. Okay, and that should be equal to how much? So that should be equal to e power minus 3t u of t convolved with derivative of u of t plus 1 is delta of t plus 1 minus derivative of u of t minus 1 would be delta of t minus 1. Now let's again use distributive property. So this is looking like x of t convolved with delta of t plus 1. So what should be the answer? X of t plus 1 means wherever there is t, we replace with t plus 1. So you get e power minus 3 times t plus 1 u of t plus 1. That is the first one. Second one would be, again this is looking like x of t convolved with delta of t minus 1. You should get x of t minus 1. So you get e, means what? Wherever there is t, we have to replace with t minus 1. So you get e power minus 3 times t minus 1 u of t minus 1. So that would be the derivative of unit step, the derivative of the output y of t. Okay, right. So next we will take one more example where we will use all these properties. Let us say, let x of t is equal to, let me say 1 for 0 less than or equal to t less than 1. 0 L. So means it's a rectangular function from 0 to 1. And also let us say h of t equal to x of t by alpha, and alpha lies between 0 to 1. Okay, so 0 less than alpha less than or equal to 1 means what? H of t is time scaled version of x of t. So let us plot h of t here. So h of t would be equal to x of t by alpha means wherever what is that we have to do. I'll just write down that. Okay, so let us first plot x of t. So x of t is a rectangle function from 0 to 1 with amplitude 1. Okay, and what is h of t? H of t is x of t by alpha. How do you plot that here? So you plot that by dividing time axis by 1 by alpha, right? This is a time scaling operation where a is 1 by alpha. So what do you get? You get 0 to alpha. So this is our h of t. Okay, so question is find y of t equal to x of t convolved with h of t. So we are asked to evaluate this one. Okay, so this we can plot. We will again plot it. So question is we have to evaluate the convolution of this rectangle with another rectangle from 0 to alpha, and we know that alpha varies from 0 to 1. Okay, so we are asked to find, this is our x of t, this is our h of t. So we are asked to evaluate convolution of these two rectangles. But if you remember our previous notes, we have seen that convolution of two rectangles we get of different width, we get what? We get a trapezoid, but those two rectangles were symmetric about each other. So first let us write down our given signals in symmetric rectangles. Okay, so if you look at this signal, first fellow can be written as a rectangle from minus half to plus half. Okay, and this fellow is convolved with the delta of t minus half. Okay, so this rectangle we can write like this. Okay, so convolution of a symmetric rectangle from minus half to plus half and delta of t minus half. So if you convolve any signal with delta of t minus half, what will happen here? The whole signal will shift to the right by half units, and hence you get this. Okay, and this fellow is again convolved with another rectangle from where to where? From minus alpha by 2 to plus alpha by 2 with amplitude 1, convolved with whom? Again delta of t minus alpha by 2. Okay, so that is the second signal. So second signal can be written in this form and first signal can be written in this form. But why do we do that? Why? Because we know convolution of two rectangles of different width will get a trapezoid, and that convolution we know that only if the rectangles are symmetric. Okay, now we got symmetric rectangles. Now by using our properties of association and commutative, so what do you get? Let us convolve the two rectangles. Okay, so what do you get? So you get a trapezoid. Okay, so you get a trapezoid from where to where? That we already know. So this would be minus t1 minus t2. That should be minus of, okay, I will draw it a little bit bigger. So you get a trapezoid like this. Okay, so this trapezoid is only the convolution of these two rectangles. So this should be minus of 1 plus alpha by 2. Correct? So minus t1 is minus half, minus t2 is minus alpha by 2, and hence you get minus of 1 plus alpha by 2. And what is the extreme time limit? It is 1 plus alpha by 2. Okay, and what are the intermediate limits here? Intermediate limits, that should be minus 1 minus of t1 minus t2. So you get minus of 1 minus alpha by 2. Okay, or I will say alpha minus 1 by 2. This fellow should be 1 minus alpha by 2. Okay, and what about the amplitude? That should be 2 times a1 a2, which are amplitudes of these two rectangles, and minimum of t1, which is 1 by 2, and t2, which is alpha by 2. So that would be equal to how much here? Because alpha is less than 1, so minimum of 1 by 2 and alpha by 2 would be alpha by 2. Alpha by 2 multiplied with 2 is alpha. Okay, so that would be the convolution of the two rectangles. Okay, now we will convolve the two Dirac delta functions. So what do you get? Delta of t minus half convolve with delta of t minus alpha by 2. So that should give you delta of t minus of 1 plus alpha by 2. Okay, so that would be the final result. Okay, and this any signal convolved with delta of t minus t naught would be what? You have to shift the signal to the right by t naught unit. So what would be the final answer? The final answer would be like this. So you have to shift this by 1 plus alpha by 2. So this point will go to origin. So finally you get the trapezoid like this. So this is 0 and this point would become alpha. This point would become 1 and this point would become 1 plus alpha. And what about the amplitude? Amplitude is alpha. This is our final y of t. Okay, and the equation of this line would be how much here? T, and the equation of this line would be 1 plus alpha minus t. So you can do that. Okay, so what is that we have done in this problem, and what is that it is asked? We are asked to evaluate convolution of these two signals x of t and h of t, which are rectangular function, but they are not symmetric about origin. So by taking the help of convolution properties of Dirac delta functions, we have found out the final answer to be a trapezoid from 0 to 1 plus alpha by 2. Okay, right. Next, same problem. Okay, second question. We'll take that as if d by dt of y of t has only 3 discontinuities. Okay, then alpha is equal to dash. That is the question. Okay, if d by dt of y of t has only 3 discontinuities, then alpha equal to dash. So first let us write down what is d by dt of y of t. So what is d by dt of y of t? You have to differentiate this signal. So if you differentiate this signal, how does the plot look? Yes, from 0 to alpha, it's a straight line with positive slopes. If you differentiate t, you will get 1 as the answer. So from 0 to alpha, that fellow is 1. Okay, and from alpha to 1, we don't have any. It's a constant signal. The derivative of constant signal is 0. And then from 1 to 1 plus alpha, derivative is minus 1. So 1 to 1 plus alpha, derivative is minus 1. Okay, that is nice. Okay, so that is the plot of d by dt of y of t. But how many discontinuities this differentiated version of y of t has? We have 4. Why? You have a discontinuity at 0, another discontinuity at alpha, another discontinuity at 1, and then discontinuity at 1 plus alpha. So definitely we have 4 discontinuities, but question is what should be alpha such that we have only 3 discontinuities. So if you want only 3 discontinuities, what should happen? This point and this point should touch each other. So if they touch each other, what will happen here? So this discontinuity and this discontinuity will touch each other, and hence they two will merge to become a single discontinuity. So what is that we have to say? If alpha equal to 1, the discontinuity at alpha and discontinuity at 1 will merge. Okay, will merge to give a single discontinuity. Okay, to give a single discontinuity at t equal to 1. So this implies we have only 3 discontinuities. Okay, we have only 3 discontinuities. So for this to happen, what should be the condition on alpha? Alpha should be equal to 1. So in that way, by using a differentiation property and also the convolution operation on Dirac delta functions, we can solve these kind of problems. Okay, actually we did not use differentiation property here, but in previous problem we have used. Okay, so next let us talk about what is called integration property. Okay, so integration property. So what does this say? Integration property. Okay, so before we talk about again integration property, let us first understand what is integration. Okay, so integral of any signal x of t is defined as integral minus infinity to t x of tau d tau. Okay, this is the way how we define integral of a signal. So this we call it as running integral. Okay, keep in mind the integral limits, they are from minus infinity to t, and we call this fellow as what? Running integral. So we call this fellow as a running integral. Okay, and we can easily prove that this fellow is linear and this fellow is time invariant. Okay, this system is linear and time invariant, I mean shift invariant. Okay, so if you draw the block diagram notation, you have x of t and then you have an integrator which is given by minus infinity to t d tau. So what will this system does? This fellow will integrate the input whatever is given. So you get y of t which is equal to integral minus infinity to t x of tau d tau, and this we call it as what? Integrator. Just like we have differentiator previously, now we have integrator. Okay, yes, now because we have said that this is linear and time invariant, definitely we can represent our output y of t as a convolution of input and the impulse response of the integrator. Now okay, it boils down to this. Yes, now it boils down to evaluating the impulse response of the integrator. So definitely if you want to find impulse response, what is that you have to do? You have to give impulse as the input. So if you give delta of t as the input, what will be the output here? We get the impulse response h of t, okay, which is equal to integral minus infinity to t delta of tau d tau, okay, which is equal to integral minus infinity to t delta of tau d tau. And you can easily see that the integral of Dirac delta function is equal to unit step function. So impulse response of integrator would be equal to unit step function. Okay, so if you want to integrate the signal, it is nothing but you are convolving your input signal x of t with u of t. Okay, so we'll write down integral minus infinity to t x of tau d tau. Correct. So this output is nothing but the input x of t convolved with impulse response of the integrator, which is equal to u of t. So integral of any signal which is defined like this, okay, is nothing but convolution of your signal x of t with u of t. So that is important. Okay, now let us come to integration property. So what does it say? If y of t equal to x of t convolved with h of t, then integral minus infinity to t y of tau d tau. So this should be equal to how much? According to the definition just now we have seen, integral operation is nothing but that particular signal convolved with the unit step function. Okay, converse is also true. If you convolve any signal with u of t, you get integral of that signal. Okay, now let us write down y of t to be x of t convolved with h of t, and this is again convolved with u of t. Now again by using association and commutative property, so this should be same as x of t convolved with h of t convolved with u of t, or this is same as x of t convolved with u of t and then convolved with h of t. You can do whichever is comfortable depending upon the problem. Okay, yes, but this would be equal to how much here? That is nothing but x of t convolved with convolution of any signal with u of t is what? That is nothing but integral of that signal. So you get here in this case integral minus infinity to t h of tau d tau, and similarly here also you get, you are convolving x of t with u of t, that's why you should get integral of that signal x of t, which is integral minus infinity to t x of tau d tau, and this fellow is convolved with h of t. So again, if you want to represent this in block diagram notation, you have x of t, and then you have an LTI system with impulse response h of t, and this is passed through integrator. Correct. Output of LTI system is what it is, y of t, and y of t is passed through integrator, and we get integral minus infinity to t y of tau d tau as the output. Now if we are asked to find what is the overall impulse response of the system, then what will be the overall impulse response of the system here, because those two LTA systems are cascaded. Note that this is LTA system, that is default, but we already know that integral operation is also LTA. So cascade of two LTA systems is again LTA, and hence overall impulse response of this system would be equal to h of t convolved with u of t. But just now we have seen that convolution of any signal with u of t is integral of that signal. You get minus infinity to t h of tau d tau. So in that way, we define the integration property of LTI system. Okay.